Hi, my name is Matthew Buello. I'm a project manager of Dogwater Design, and today I would like to tell you about our company's design of the TechSmith headquarters facility, as well as a wastewater treatment system design, both on MSU's campus. Presenting with me today, we have Rodrigo Azevedo, our transportation engineer, Troy Dowdy, our pavement design engineer, Zach Gentry, our hydrology engineer, Mike Brown, our structural engineer, as well as members of our environmental engineering department, Hunter Lee and Harrison Sochar, who will be talking about the wastewater treatment system. For those who don't know, TechSmith is a software development company specializing in screen recording products like Camtasia and Snagit. And prior to the pandemic, they had multiple locations in the East Lansing area. With these multiple locations, there was an issue for employees working at separate buildings to work collaboratively. Additionally, there was a high cost for maintaining these facilities. So because of these issues, TechSmith decided to consolidate. And with land granted to them through the MSU Foundation, they obtained 5 acres at the corner of Harrison and Crescent Road, along with their 300 employees and a hope to attain a facility at $15 million. So with these items, we decided to design a facility for these employees that would adhere to MSU's campus master plan, providing multiple transportation options for cyclists and pedestrians, as well as public transportation, as well as minimizing developmental impacts on the Red Cedar River watershed, in addition to utilizing low-impact designs and sustainable practices. So with that being said, we're going to get into the design.
Transportation. In the transportation side, we designed the site plan for the new facility, and we also designed the traffic impact study. The site plan, that's the parking lot, along with walking and cycling facilities and access to the public transportation network of the Lansing area. As for a traffic impact study, that's analyzing how the new traffic, mostly vehicle traffic, will impact the current road network in and around the MSU campus and the East Lansing area. For the traffic impact study, we analyzed the 2 closest intersections, so the South Crescent Road and Harrison Road intersection, and the North Crescent Road and Harrison Road intersection. For the site plan, we included parking facilities and other forms of transportation, such as walking, cycling, and bus. And all of these were met by the City of East Lansing zoning code, and they also include sustainable and LEED certified options based on the points system. So for the parking lot design, TechSmith currently accounts for 300 employees. This is a number that was given from the company to us. It is projected to increase to 400 employees in a 20-year period, and that's the 20-year design period we're going to be using for the traffic impact study. The parking lot also includes handicap spaces for both cars and vans. So the total amount of spaces in the parking lot is 295, and there are going to be 8 handicap spots. 6 for cars and 2 for vans. There will also be addition of electric vehicles and charging spaces. This will be 10 total. Also, we're going to be adding new sidewalks in and around the parking lot for safety and ease of access. And the whole facility will have 1 access point, a driveway on its west side connecting to South Crescent Road. We'll also include trash collection and shipping and delivering facilities. For that, we had to determine if single unit trucks can fit around the parking lot. We use single unit trucks since there are not going to be many deliveries to the facility, as TechSmith, the client, has told us. So for walking and cycling facilities, including the public transportation side, we are widening the current sidewalk on the west side of Harrison Road to 10 feet. This is creating a new shared path with bicycles. That will also lead to a new shared path from the Harrison Road sidewalk into the entrance of the building. We're also including bicycle facilities and bicycle parking next to the entrance of the building. As for public transportation, CATA, which is the Capital Area Transportation Authority, currently provides bus services on both directions of Harrison Road. This is a northbound and a southbound connection. There are 2 lines at the moment, as you can see here on the map. Around the red diamond where the new building is, there's line 18 and 20. And these connect to both the MSU campus, the East Lansing area, and also South Lansing. And lines around that region. Of course, there's two bus stops. One is north, one is south. The northbound is a bit far from the facility, but the southbound one is right next to it. So we're adding a new sidewalk connecting to it. This is the site plan. So mostly the parking lot, as you can see. There are 5 rows of parking spaces with 24-foot wide driveways around it. This allows for a good flow of traffic, and also allows for enough space for a single unit truck to be able to maneuver around each corner. As I mentioned before, there are 295 total spaces, 8 handicap spaces, 10 electric vehicle spaces. The total area of the facility for the parking lot is 128,000 square feet. And all of these were designed to be able for water to be drained and no flooding to occur. As you can see, there are sidewalks that go around the center, the west, and the east side of the parking lot. So this, again, for safety and better movement of pedestrians. You can also see the shared path along Harrison Road with the connection to the bus stop. And you can see a new shared path all the way up to the entrance of the building next to the bike parking facilities. On the west side, we have the delivery and shipping facility with access to the one driveway. And on the northwest side, we have the garbage and trash disposal facilities. And you can also see the handicap spaces and the electric vehicle spaces next to the facility, along with the required fire lane for emergency services in case they're needed. So for the traffic impact study, that's how we analyze how the new traffic will impact the road network. From that, the team has determined that of the new traffic, 70% will be heading north on Harrison Road from the site, and 30% will be heading south. 70% going north, that's the majority of traffic. That is due to the MSU campus being close, due to downtown East Lansing being north on Harrison Road, and due to the Trowbridge Road interchange with I-496 and US 127 being north of the site, which will lead traffic to the downtown Lansing area. As for the 30% that go southbound, as you can see, we have traffic using the Dunkel Road I-496 interchange that goes to South Lansing and Okemos, as well as using Mount Hope Road to connect to the current Okemos and Hazlet area. We also accounted for the fact that the current TechSmith headquarters is in Okemos, so we would assume a large percentage of cars would be going that direction, since that's where they currently work, and is assumed to be living next to the facility or in around that region. Again, not as much as the 70% that will be going to East Lansing and downtown Lansing. For the traffic impact study, we use Synchro 10 software, which allows us to model an intersection, so we can put the traffic counts based on approach. So for each of the 4 different directions in an intersection. And from that, we can calculate the level of service and queue length per movement. And as you can see here on the right, a screenshot from the Synchro software, you can see each different approach based on direction. So eastbound, westbound, northbound, and southbound. And that gives us the level of service. So D, C, A, and A. And on the bottom here for the stoplight, we can see the signal timings that are given. So the level of service means that's the quality of traffic based on the traffic flow of the intersection. So how much of traffic is actually flowing. And that goes from A, B, C, D to E and F. So anything above a D is considered acceptable. That is where it's approaching unstable flow, but it's not completely unstable, as you can see here on the picture. So it's close to being unstable, but it's not there yet, so it's still acceptable. And we use that to determine the traffic flows on the North Crescent Road and the South Crescent Road intersections with Harrison. For that, so by analyzing the level of service, we realize that there's a level of service E at the intersection of South Crescent and Harrison. So for it to be more flowable, we determined that of the traffic that's coming out, 50% will use that intersection, while the other 50% we will use the North Crescent. This is because there's already a stoplight at the North Crescent intersection, and this will allow for drivers to feel more comfortable and have an easier time going left on here. And then if you look at both the intersections, you have North Crescent here and South Crescent on the bottom. Both of them have their own dedicated turning lanes. So for northbound traffic, the left lane. And with that, we determine that there's enough storage length, there's enough length of the turning lane where the queues or the amount of traffic will not be impacting the overall traffic flow of the intersection. So for example, North Crescent, the left turning movements, there's not a long enough line or queue for it will impact the through and the right turn movements. And from that, we determined that the only changes needed were signal timings. So the green light for the left turn movement will be increased by 1 second, meaning that the through light will be decreased by 1 second. The overall cycle is still the same. And then for the southbound Crescent, nothing will be done. It will still be a stop sign. And then, as you can see, there's no change to the actual geometric layout. Yeah, so thank you. And that was the transportation side of the project.
Hello there, my name is Troy Doughty. I did the pavement systems design for the TechSmith headquarters. So there's quite a bit to cover, so we're going to jump right into it. We'll start off with data collection, the design, the cost analysis, and the final design and cost for the whole thing. So starting off, the environmental acknowledgement. There are a lot of carbon emissions that come from the construction process. So we want to make sure that we're not using excessive materials that release greenhouse gases. So we do that by maximizing the process and making sure that we're meeting that 20-year design life for this project, for this pavement, without using extra materials. We're going to be using recycled aggregate in the new parking lot as well as in the HMA for the final design. That's going to save us cost, but it's also going to save having to ship in new aggregate. We can just reuse old aggregate from torn up concrete, that sort of thing. We're also going to be adhering to LEED requirements and getting as many credits with them as we can. And then protecting the surrounding environment from erosion, chemical damage due to runoff. So that means our grading is done correctly and our curb and gutter is done correctly so that we don't have any material or anything running into the Cedar River that's right there. We want to make sure we're protecting that environment. So what's the scope of work here? We're looking at Harrison here going north and south between Trowbridge at the top and Mount Hope at the bottom. And then we have the main parking lot where the building and everything else will be. Then we have Crescent Road going around and Middlevale going around here. So it's a lot of pavement to cover, but we feel it's necessary for this design because it's all going to be part of the surrounding environment for the TechSmith building. It's all going to play a role in the presentation of that building. So then moving into permits, we have the right-of-way, we have the driveway permit, and then soil erosion sediment control. I won't go into these too much just because I don't have the time, but if you need, go ahead and pause, look at these, digest a little bit, but these are the permits we're going to be needing. So where did I start with the design for this project? What was the methodology? And the first thing I started with was who has jurisdiction of the roads, because this informs the design regulations, the codes, the limits, the layer thicknesses. It's all very important to know what our limits are before we start. So we don't design and then realize, oh, we actually can't go that thin. We need to redesign. So Harrison is under Ingham County, Crescent, Middlevale, and the parking lot are under MSU jurisdiction. So what are some of the solutions we can use for these roadways? And we have three main alternatives: rigid, flexible, and mill and fill alternatives. There is overlay, but it ends up being too expensive due to the fact that we need to redo all the curb and gutter. So we just eliminated that entirely. Mill and fill does effectively the same thing, but is much, much cheaper. So moving on to data collection, we're going to go from data collection to the design to cost analysis. But starting with data collection, we looked at the subgrade and the soil conditions. So this is important because the entire roadway sits on this soil, on this bed, and it's the foundation for the roadway. And so if it has weak areas, areas that are too firm, areas that are eroding, we need to know that so that we can fill it with proper soil. So how do we check out those soil conditions? Is by using borings and the standard penetration test to determine the mechanical characteristics of that soil. So resilient modulus in this case. Data collection part 2 is going to be the subsurface conditions and surface conditions. So we can visually examine these roadways to determine these things. And what we see through our observations is that there's thermal fatigue and alligator cracking, but there aren't any pits, which means that the subbase and the base, the roadbed is all healthy. So it's only that top course that's failed so far. So our conclusions: surface is unhealthy, subsurface is healthy, which means we can reuse it, and the ride quality is poor. So those are all design elements that are going to go into it later. So data collection part 3, traffic conditions. It's pretty obvious. The more traffic a pavement gets, the more wear and tear it goes through. And the currency for this is ESOLs. So that's done using an equation and a formula. But what we came across was this table here that for rigid and flexible, we have different values. These all go into the design inputs that we'll get to in a little bit, but the traffic volume is very important. Final data collection is the climactic data. This has a large effect on pavement. Michigan goes through a lot of rapid temp changes, which causes stress within the pavement, starts microfractures, which turn into actual fractures, which turn into cracks, etc. Freeze thawing is a big proponent of this, or it's a big motivator for this, because ice forms and then it grows, creates stresses and cracks, causes the pavements to fail, which is why we cannot use a porous top course. It allows too much water through. That's the whole point, but that's also the issue. So we have the PG grade listed for all the techie guys out there, guys and girls. So moving on to the design aspect of this. So with all of those design inputs, we can put those into ASTO 93 and the Asphalt Institute methods to get these outputs. It's a very simple, put your values in, get an output. So again, we have recycled aggregate, eco-friendly, 15% cheaper or so. You'll notice with Harrison for both flexible, for just flexible, I mean, we have a 5E3 top course, and that's because we want a higher quality for the higher demand that Harrison has. Whereas Crescent and Middleville will only get a 5E1. It's a little bit cheaper than 5E3, and it just doesn't need the extra strength from 5E3. Mill and fill will require 3 inches of cold milling and an application of 3 inches of HMA top course, which we'll get to. So moving from the roads to the parking lot, there are a few elements to the parking lot. There's the actual pavement, there's the sidewalks, there's the curb and gutter, disposal slab, and driveway and loading dock. So you can see those on the map, pause if you need to. So the actual pavement design of the parking lot just came from MSU IPF. You can see that here. Nothing really too complicated. We replaced the top, or not replace, but we use an LVSP for the surface course because we figure the parking lot doesn't get a whole lot of traffic volume. It's mostly just cars sitting. So we don't need the expense of another type of HMA. And then of course, we're using our recycled for the base. Moving on to the sidewalk, again, just came from MSU IPF, just a 6-inch slab for the concrete for that sidewalk, and then a 2-inch class 2 aggregate base. Curb and gutter from MSU again, don't really need to go into it, but it's here. It's something that was designed, something's going to be used. The disposal slab, it's very similar to the sidewalk in that it has that aggregate base, but instead of being a 6-inch slab, it's going to be that 8-inch. And that's so it can handle the load of that, the dumpster being there, and also the vehicle pulling up to empty the dumpster, and he's able to handle that load over time. But again, doesn't need to be anything crazy. It's not getting traffic. The final element of the design is the driveway and dock. So this needs to be able to handle standing traffic because it is a dock. And so heat and pressure can cause asphalt to run. And that was the driver for choosing concrete in this particular case. Another benefit of concrete is that it requires less repairs over time, whereas HMA needs to be repaired relatively frequently. And we'll see that in a little bit. So moving on to the cost analysis using LCCA, which is a life cycle cost analysis, is what it's called. LCCA takes the initial material and labor costs from the design and accounts for inflation, fuel consumption, maintenance costs, all sorts of different things that come after you've actually put the roadway in. So the final cost to construct the pavements will be greater than that initial cost of just the labor and the materials. So moving on to some maintenance details, you'll see for flexible, rigid, and then additional general costs, there are different pricings. You can see here flexible just uses more maintenance over time, whereas rigid only needs a couple of different maintenance elements. So MDOT has provided these particular values, and then we use them in that LCCA. So final thing for cost analysis were the actual results. So the key thing to take away here is that these yellow bars are referring to the mill and fill final pricing after that cost analysis has been done. And we can see that mill and fill is by far the cheapest over flexible or rigid new pavements for all roads. So mill and fill is definitely the most applicable option here, but is it going to be better than the new construction? Is mill and fill a viable option? And we say yes, because the subsurface conditions for Harrison, Crescent, and Middlevale are healthy. We don't need to tear up that road bed at all. We don't have to go down to the soil and do the soil or anything like that. We can leave it as is. We can simply cold mill off that 3 inches, lay the 3 inches of HMA on top and call it good. The new construction really doesn't offer any other benefits. We just can't justify the cost for that. So final design recommendations is that Harrison Crescent and Middleville will all receive a 3-inch mill and fill, as I stated. And then here we have sort of a reposting of all of the different design graphics from before. So final design cost is going to be somewhere around $2 million. So on this table, you can see each of the project elements and their initial costs. So you can see all the elements of the parking lot, all the different roads we're redoing. And so you have that initial cost and then your final cost after the LCCA. So you can see it jumps from just about $1 million even to $2 million. So that's going to be the final design cost for the project. I hope you've enjoyed the presentation and it's been helpful.
The hydrology portion of this design project for the TechSmith headquarters on Harrison and Crescent Road focused on managing the stormwater that would run off of the site and enter the Red Cedar River water system. Managing this water is necessary as it deters the transportation of pollution and pollutants from sites of human activity such as construction and buildings into the water system and further downstream. Additionally, the impervious surfaces that human activity will add to a natural area will increase the amount of runoff that will leave the site instead of entering into the groundwater as natural. This can result in severe flooding that can have severe consequences on people and their property. Legally, we were required to have a 0.15 cubic feet per second per acre drained, with a flow of 3 to 10 feet per second in each pipe, while being able to handle the volume of water delivered by a 100-year 24-hour storm event. The system was designed with the objectives of meeting all the legal requirements, but also meeting a pleasing aesthetic to passersby on the street or sidewalk. Obviously, the primary goal was also to protect the natural environment, and so I opted to do this by handling all the stormwater on site and not discharging it into an external system. This model was designed by EPA SWIM 5.1, and on the left image, you can see 5 drainage subcatchments overlaid with the system structure. And on the right, those same 5 subcatchments with the pipes that will convey the stormwater through the system. The pipes were sized according to the flow values in the pipe as determined by the rational method, which is described in the equation Q equals CIA. For the runoff coefficient value C, a weighted average was used as each subcatchment had different surfaces the water would run on. Table on the right shows the averages and the final C values for each subcatchment. Next, the NRCS Engineering Handbook provided velocity equations, which provided the velocity in each subcatchment, and the length of each subcatchment was measured, and the time it would take to travel the length of the subcatchment was determined. This was used in consulting an MDOT rainfall table to determine the intensity value that would fall over a given subcatchment during the storm event, which we are looking at. The table on the bottom summarizes the flow values for each subcatchment. These were then entered into pipes and summed accordingly, and then Manning's equation was used to size the pipes. All the pipes are to be made out of corrugated plastic, resulting in an N value for their roughness coefficient of 0.009. Using Manning's equation resulted in the diameters for each pipe shown in the highlighted column on the left. However, these values are not commercially available for piping systems, so the next largest commercially available size was chosen. On the schematic on the bottom, the pipes that will correspond to the diameters and the diameters of those pipes, as well as their area, is shown. Using the relationship between the flow rate and the area, the velocity in each pipe was calculated and those results are found on the column on the right. All of these values fall within the 3 to 10 feet per second legal requirement set forth by the Ingham County Drain Commissioner, satisfying that requirement. The infiltration basin was selected as the outlet for the stormwater system, as the infiltration basin allows all the water to infiltrate into the groundwater system, and it does not need to be discharged into a river or into any other storm management system, achieving my goal of wanting to handle all the stormwater on site so as not to create any strain anywhere else. The Ingham County Drain Commissioner requires by his equation that it can hold the volume of this storm, which for this problem was 139,000 cubic feet. Designing a 200 by 70 ovular shape with a 10-foot depth provided a volume of 140,000 cubic feet, providing extra room as well as meeting the requirements set forth by the Drain Commissioner. The 10-foot depth was selected, even though this is larger than the average infiltration basin, because the type C and D soil conditions make infiltration in this particular area difficult. To compensate for this, the basin was over-excavated by 3 feet, and drain tile should be laid at the bottom of it. This will improve its ability to infiltrate and ensure that the basin does its job in managing the stormwater. An additional 1 foot of freeboard is added, bringing the depth to a total of 10 feet. Additionally, it was placed 25 feet away from the parking lot and the nearest sidewalk, such that in the event that the basin were to overflow, it would have a minimal impact on property and people. A rain barrel is also included in the design to catch the rainwater from the roof of the headquarters building and recycle that into non-potable gray water fixtures, such as restroom fixtures and lawn care maintenance. One 100,000 gallon tank will hold this water, and this was designed to be extra. It was not factored into the equations of the basin, and thus it is not necessary to manage the stormwater, but it would be a good addition to improve the environmental impact that this building will have. Overall, the final design is summarized on the image of the right, with the sized basin placed where it will be 25 feet to the north of the parking lot, and the 100,000 gallon tank placed where it will be in the southeastern corner of the building. All the pipes are shown. This design met all the goals and requirements, and by my estimates will cost approximately $203,000 to construct. Thank you.
For the structural design of TechSmith headquarters, the building itself is roughly 36,000 square feet and stands at 30 feet tall. Their new headquarters is designed to support the change in work styles due to COVID-19. This means accommodating for a mix of in-person, hybrid, and remote work capabilities, as well as wanting to have infrequent gatherings of their entire staff of 300 plus employees and growing. In addition to goals focused on the staff work capabilities and the structure's functionality, TechSmith has also set out to achieve a gold LEED rating for their new headquarters, and this entails incorporating several environmentally friendly practices into the building. This includes roof solar panels, which provide green energy, a green roof, which offsets their carbon footprint, as well as runoff water from rainwater, and the orientation of the building itself is fixed with its long ways going east-west, so that their south-facing windows, which cover the entire south face of the building, can allow the maximum amount of natural sunlight to come in through their building. The client has also specified an offset alignment of the first and second floor, which allows for a patio space. To achieve all of the goals that TechSmith has set out for Dogwater Design, the building has been designed in the software Geopack. Here are the structural plans for the level 2 design. It's split into A and B areas on the plan. The level 2 design has a typical floor framing that is mostly consistent over the floor, but it does have some uneven column and beam placement between the A and B areas on the north side of the building, which accounts for columns that extend down from the roof to the second floor ceiling that are not visible in these plans. As for the floor itself, the floor slab was chosen from the Volcraft steel deck manual, and the floor was required to have a rigid composite deck for the concrete slab. As for the patio, which is on the second floor, its deck will consist of 2-inch thick concrete pavers. The frame, apart from its own superimposed self-weight, supports high live loads from the office staff, which comes and goes on a daily basis and does their work, and also high dead loads, which account for computers, equipment, furniture, etc., all kinds of things. And so these gravity loads were factored both into the design of the frame, but also in the choice of the floor slab, because the floor slab needs to be able to support these gravity loads. The roof consists of non-composite metal deck, plywood, and insulation. For the roof design, the roof framing itself also has mostly consistent column and beam placement throughout its entirety, with the exception of the skylight and the roof hatch, which both mark an absence of beams. The roof may not account for the same live loads as level 2 does, because the staff is generally not on the roof, and there are usually only a couple people up there at a given time for maintenance of, say, the solar panels or the green roof, but it does account for a lot of special features which all have their specific loads listed on the slide. The green roof covers completely east of column line 6 on the plans. This consists of soil and plants which are maintained throughout the year, as I said, to minimize the carbon footprint, and are also incorporated into the drainage system, which reduces runoff water from storms, rains in general. The solar panels cover the roof completely west of the column line 6, and then there's also, of course, the roof hatch and the mechanical unit to account for. Though the roof itself doesn't account for the same live load that level 2 does, there is another kind of live load that it does account for that level 2 does not: the snow load. Whenever it snows, the snow load applies to the roof, but it also applies to the second floor patio, which is on the plan shows as is treated as a lower roof for calculation's sake. But the patio also accommodates for snow drift loads, which accumulate against the building as a sort of incline from snow being blown against the building due to the wind. The roof itself does not have to account for snow drift loads, because the roof, whenever snow is moved by the wind, it's simply blown off the roof. As for the design of the structural members themselves, all of the members are made of A992 steel, which have a yield strength of 50 KSI, and all of the members were selected using the American Institute of Steel Construction manual. The first members that were designed for were the beams, which were designed by analyzing a single bay on each level and applying it to the beams on the rest of the level. A typical bay has 30-foot spacing between the columns north, south, and east, west. It has 5 spans which point north, south, and then 2 girders on either side pointing north, south, and east, west. On the slide, you can see that there are loading diagrams, and these loading diagrams list the typical loads that are applied to each level. These live and dead and superimposed dead loads were all combined into factored loads, and these were used for the strength design of the members. So for the strength design, the requirements included calculations for bending moment and shear force, which were relatively simple to satisfy because they're both physical qualities of the members and can be found in the manual itself after some calculations. But what was a lot harder to satisfy was the serviceability requirement, which is the amount that each member is allowed to bend. In order to choose the correct member, instead of testing for the deflection member after selecting a member, which is general protocol, usually you do bending moment and shear force, and then you select a member, and then you test for the serviceability. Instead, I was forced to go backwards. I focused on choosing an adequate moment of inertia, which is the physical quality of the members that I knew would satisfy the deflection requirements, and after that I went back and checked for the bending moment and the shear force. And as you can see on the slide, you can see all of the members that I chose for the beams, the columns, the X-brace, which I'm getting to. The columns next. For the column design, the columns are typically 15 feet from floor to floor. The inside ceiling is set at 12 feet, which is typical of an office building, and above the ceilings is a 3-foot allowance for the space of the structural frame, mechanical, electrical, plumbing utilities, and the ductwork. I focused on designing the first floor columns because they carry the heaviest weight and need to be the sturdiest, and then I extended the design for those all the way up to the roof. I did this by taking typical loads from the roof, the second floor, and the first floor over a tributary area and combining them into one load that the column needed to support. After that, I found a member that was sufficient in the AISC manual. Separate from these members' design, the building also has a lateral load resisting system, which is designed to resist against the wind loads that are applied against the building every day. For this, the X-brace system was chosen and designed for. This brace spans from the first floor to the second floor, and then the second floor to the roof, and was designed separately using a software called SAP 2000. For this design, trial and error was the main method that I used. I started by using the same members that the columns are made of and ran them through the software, simulating all of the loads and deformations that they would be subjected to. From here, I continuously changed and adjusted the X-brace members time after time until I landed on a double angle member that satisfied the simulation, which is also listed in the slide. So that concludes the overview of the structural design.
Now that we've talked about design aspects, it's important to bring up the construction process. The first step in the construction process is obtaining permits for the multiple construction tasks. These permits are governed by organizations ranging from the City of East Lansing to Ingham County to the state of Michigan. Obtaining these permits is a fairly straightforward process of either application approval or application inspection approval. The difference between the two is that the application approval can be done by either the engineer or the contractor, where the applicant must also provide engineering drawings or design details before obtaining the permit. The application inspection approval should be done by the contractor before the completion of the construction task. This is the case for the roofing permit. Failure to adhere to the standards of the inspection will either result in reinspection, reconstruction, or redesign. Any of these will result in additional fees, extended duration, and increased costs of the project. So it is important to note the permits required. The cost of the construction project is estimated to be $19 million. The largest portion of the construction cost is the facility itself. This includes the structure, the mechanical, electrical, plumbing, and HVAC systems. The second largest cost is the paving and grading. Additionally, we have included 10% engineering fee for all of the construction tasks, as well as a 10% contingency on the engineering and construction tasks. The contingency is to allow for any unforeseen circumstances. The remaining aspects of the construction equated to roughly 3% or $400,000. The construction process is estimated to start in late February of 2022 with geotechnical earthwork and grading. Geotechnical earthwork includes cutting trees, clearing land, as well as staking and marking the area. Upon completion of the earthwork, we will then begin with the foundation. The foundation is estimated to last 11 weeks. Upon completion of the foundation, we then begin with the structure, the longest duration of the construction process, at 42 weeks long. Grading includes grading of the land as well as preparation of adjoining roadways. This is set to last 3 weeks. And upon completion of grading, we will then begin with paving. Paving, additionally, is 3 weeks long. Concurrent with foundation work, we begin with the retention basin, and stormwater sewer network. The combined duration of these two tasks is 9 weeks long. And upon completion of the stormwater sewer network, we will then begin landscaping for the facility. This is the second to last process.
Hello, my name is Hunter Lee, and my partner is Harrison Shore. We are environmental engineers for Dogwater Design. For the past 4 months, we have been working on a separate project creating upgrades for East Lansing's wastewater treatment plant. As technology advances, new and more sustainable technologies are made available, and the desire for a more sustainable system has created a need for treatment sites to upgrade in order to meet the changing effluent guidelines. The scope of that, what we have been tasked to complete, is to increase the amount of nitrogen, phosphorus, and carbon reclaimed from the system, as the city will be changing the nomenclature of the plant from a treatment plant to a resource recovery facility. To understand the current layout and process for the East Lansing treatment site, a model was created using information provided by the City of East Lansing. The software used for both the baseline model and the technical design is named Sumo and is capable of modeling wastewater systems under different parameters.
To help East Lansing convert its current wastewater treatment facility into a water resource recovery facility, several design parameters were included, starting with an integrated fixed film activated sludge system, which is used for improved nitrogen removal. Following the IFOS system, an anaerobic digester unit is to be included for energy recovery, usually in the form of methane in this case. And lastly, any biochemical or chemical additions other than ferric chloride, which is in the current system, can be added for increased phosphorus removal. Attached here are effluent guidelines and limitations provided by the EPA, most notable of which being nitrogen, phosphorus, and sludge retention time. The nitrogen concentration in the effluent should be less than 2.5 milligrams per liter, phosphorus with less than 1 milligram per liter, and a total plant sludge retention time of 15 to 20 days. Several influent parameters were also provided to represent the wastewater that enters the facility each day, with contaminant concentrations of total nitrogen being 45 milligrams per liter, total phosphorus having 10 milligrams per liter, a chemical oxygen demand of 220 milligrams per liter, and a flow rate of 18.75 millions of gallons per day.
My technical design is as follows. The upgraded model is created off the baseline model shown earlier. The main focus is after the primary clarifier, where the flow is treated with ferric chloride for phosphorus removal. The current aerobic reactor that's already on site will remain in place, and 2 additional reactors will be included, an aerobic reactor and an IFAS system. The flow remains the same as in the baseline model headed towards the secondary clarifier. The sludge is then collected from the clarifier and sent to the newly added anaerobic digester. The sludge goes through all 4 phases of anaerobic digestion before the remaining sludge is removed and the gas is sent to a tank for storage. Utilizing the current technologies available on site and the newly developed technology, we can increase the amount of nitrogen, phosphorus, and carbon removed from the flow. The technologies added are shown below and were modeled in the design above. The IFAS model and the anaerobic reactor are both used for increasing the amount of nitrogen removed from the system. The IFAS system has a reactor volume of 8,500 meters cubed per chamber with 4 chambers, and the anaerobic reactor used to prime the IFAS system has a volume of 10,000 meters cubed and a tank depth of 10 feet. The anaerobic digester has a volume of 2,000 meters cubed per chamber and 2 chambers. The anaerobic digester is used for carbon removal in the form of methane. The ferric chloride addition is 2,000 kilograms per day, and the use of ferric chloride is to remove phosphorus. The current system already is using a lower dosage of ferric chloride for phosphorus removal. The effluent values can be seen below. The main focus for the scope of the design is the effluent nitrogen at 2.34 milligrams per liter and the effluent phosphorus at 0.86 milligrams per liter. The sludge retention time is 30.32 days to increase the amount of time the reactors have to promote ammonia removal. Biological oxygen demand, pH, the total suspended solids, and the dissolved oxygens are at acceptable levels according to the effluent guidelines. Carbon is removed in the form of methane, one of the main focuses of the design. The results show that the digester was able to create methane at a rate of 93%. The gas is collected in a gas tank, and the total amount created per day can be found to be 1,528 meters cubed of methane per day. The cost of the newly upgraded plant can be seen below. The cost of the chemical addition, ferric chloride, is $233 a day, and $10,100 is the estimated cost for the daily upkeep and running of the plant per day.
Building off a base layout of the current East Lansing wastewater treatment plant, several new units were added for increased contaminant removal, including an anoxic reactor, an anaerobic digester, chemical additions such as methanol and ferric chloride, and a simple CSTR, or continuous stirred tank reactor. Images of the most notable units added to the treatment system can be seen to the right. Starting with the anoxic reactor, it had a volume of 12,000 meters cubed per chamber with 2 chambers. This was coupled with the already existing aerobic reactor to perform nitrification and denitrification. Next, an anaerobic digester was designed with a volume of 6,000 meters cubed per chamber and included 2 chambers. Chemical additions were also added. A ferric chloride dose of 1750 kilograms per day was included, along with a simple continuous stirred tank reactor to ensure mixing for phosphorus removal. For further nitrogen removal, a methanol dose of 11,000 kilograms per day was included in the design. The results from this design were obtained from a 100-day simulation through the Sumo 21 software. The effluent levels of nitrogen were 1.2 milligrams per liter, which was less than the limit of 2.5 milligrams per liter. A phosphorus level of 0.83 milligrams per liter passed the limitation of 1 milligram per liter, and a dissolved oxygen of 0.27 milligrams per liter was well under the limit as well. Lastly, a plant sludge retention time of 15 days fell within the 15 to 20 day limitation. A breakdown of the daily costs associated with this design are included in the table. This design resulted in an operational cost of $17,880 per day. With the chemical additions added as well, the total cost of this operation ends up to be just over $25,000 per day.
These designs can provide the city of East Lansing with increased resource recovery and provide an effluent that meets guideline parameters. Possible profits can be made in the capture of methane through use of selling or as energy in the system. The sludge that is removed from the system instead of being disposed of can be reclaimed. The phosphorus and nitrogen have possible agricultural or industrial uses. Overall, these upgrades will increase the quality of water for the city of East Lansing.
With the time that we have left, I would like to thank the people who made this possible. I would like to thank Professor Anthony Engel for giving us the opportunity to design this facility. I would also like to thank Dr. Hayter, who aided our design of the pavement sections. Additionally, I would like to thank Eric Dickinson, who aided our structural engineer in the design of the facility. Also, I would like to thank Mr. John Engel, who aided our transportation engineer in his design and traffic impact study. I would like to thank Dr. Lee in his aid of the hydrologic engineer design, as well as Syed Hasham, who aided the environmental engineers in their design of the wastewater treatment system. Thank you to those people previously mentioned, and thank you for watching.